So I thought we were doing ice tables today. That's coming early next week. But we're still going to lay the foundation for, we're kind of going to be talking about it in theory. That's kind of like the idea is, we'll talk about something in theory and then we'll kind of show you a mathematical way to kind of speed up the process. So just a few things to review. What is equilibrium?
The forward and reverse reactors equal each other.
Okay. What's the book's definition of that?
When the
The what?
they stop changing.
Okay. When they stagnate, they stop changing, or the science word would be when they remain constant. Okay? And then we also talked about how that could mean that they are equal, but it's very unlikely that the concentrations are equal. Why is that?
Because they're different size particles and they're made up of different amounts of atoms.
Just for sheer probability purposes. There's only one position where you would have equal concentration, right? And there's probably an infinite amount of positions where you could have differing concentrations. Yes?
Yes.
Okay. So let's kind of apply this. We're actually going to talk about rate a little bit again today. Before I do that, I don't know what's on the next slide. Okay, not going to do that yet. Okay, knowing the equilibrium constants quite valuable for quite a few reasons. It can allow us to figure out the tendency of the reaction. What I mean by that is how likely products are going to form, how much products are going to form, how little products are going to form. Okay, if you're given a set of concentrations, you could tell if you're at equilibrium or not, and if you're not at equilibrium, which way it would have to shift for you to get to equilibrium. There's a lot of things that the equilibrium constant is going to tell you. Okay, and we looked at yesterday how you can have an infinite amount of what, but always the same what. Restate that. You can have an infinite amount of what, but always the same what? Infinite amount of equilibrium positions, but only one equilibrium constant. When I talk about equilibrium positions, what am I referring to? What the concentrations are at equilibrium. Because we talked about if you change the starting amount of concentration, you're going to have different equilibrium concentrations, but you always have the same what? Constant if you're assuming you're at the same temperature. So, let's look at this guy. Do you have any space or no?
Yeah.
Like, hey, here you go. Yep. So we're going to do this. Got a little double arrow equilibrium going on here. Let's say we knew the equilibrium constant of this to be 60. Okay? The question we should ask, after it comes to equilibrium, or reaches equilibrium, what will the system look like? So we would know, and these are all gases, by the way, just I didn't put that in there. But so if I were to write the equilibrium expression, I gave a nice 1-to-1 ratio so we don't have to think too hard about it. So we know this. Okay? So this is going to lay the foundation for what we're going to do with ice tables. So your ability to understand this kind of concept here will help you starting next week. So let me ask you a question. Is there anything that you could deduce about the reaction from that constant? You don't have to think. That's something we like to do all the time. The products are greater. Very good, Grant. I mean, it's not like it's
sarcasm?
no. I mean, I'm just kind of shocked. Usually, when I ask questions that you have to think a little bit, you guys stare at me like, you know, a cow about to get hit by a train. Yeah. But being able to look at something and make an inference about it is a really good skill to have. Looking at, I know it's not like overly complicated because you probably know math well enough to know that if you got a number greater than 1, what does that tell you about the top portion of a fraction? It has to be bigger. Okay? Well, if we know that these are our products and these are our reactants, we know that we have to have, at equilibrium, more products than reactants. Okay? So, we're going to assume something. Well, not assume, but we're just going to say we've got 9 molecules of this. And we've got 12 molecules of this. And 0 molecules of my product. Okay? So we know from the fact that we have all reactants and no products, we know that it's going to start reacting and shifting to produce more products, which means that the forward reaction will be faster than the reverse reaction. Make sense? Okay? But we don't know how far it's going to go. We have an idea that it's going to be product favored, but we don't exactly know when it reaches equilibrium what the concentrations are going to be, but we can predict it. You'll find later that that initial conditions refers to the I of our ice table later. And the new conditions, assuming we're at equilibrium, or we would say equilibrium concentration, that would refer to the E of our ice table, but we'll get to that come next week. So we're kind of setting the ground, you know, setting the foundation here. So I'm just going to say I've got my O3, my NO, my O2, and my NO2. Okay? At the very beginning, how many molecules of O2 did we say we had?
0. O3.
O3, sorry. My bad. NO?
12.
And the other guys?
0.
Okay? Now, we know that everything's a 1-to-1 ratio. So maximum, what's the total amount of molecules will react? What's that? Of one type of molecule, maybe I should say that.
9.
Is it 12 or is it 9?
9. 9. So it
It's
can't,
definitely 9,
yeah, 'cause it can't go more than 9.
right? If one molecule of this reacts with one molecule of this is going to run out after 9 gets used up, right? And even though I've got 12 of this, right, that should make sense. Limiting reactant idea, okay? So let's just say, I don't know, we know that the products are favored. So let's say we react 6 molecules of that. So we're going to say, we started with 9. Now, if we react 6, am I going to add 6 or remove 6 from O3? Remove 6. So I have 3 molecules left over. Started with 12, I reacted 6. Why 6? Because it's a
It's the one you used last time.
1-to-1 ratio. Okay, if that was 202, that would be 12. That makes sense? And I started with 0, and I subtract 6. Add 6, right? Why am I adding 6 here?
Being produced.
I'm being produced, okay? I'm sorry if I'm asking questions. But I'm not.
Did you just choose 6 or?
I just randomly chose 6 because now we'll get into. I'll show you in a sec how we could potentially get into a mathematical way of doing this. I'm just setting the stage here. So now what we can do is we can take these numbers, plug them in here, and see if they equal 16. And you probably have already made the distinction that the answer is no. Okay, so I would do my O2 is 3. That's not right. My O3 is what I want. No, my O2 is 6, sorry. 6. My NO2 is 6. And then 6 and 3.
So it's
Is that going to give me 16?
No, it's 3. 36 divided by 18.
Give me 2, right?
2, you're right.
Okay? So we are product favored here, but we're not product favored enough for us to actually get to equilibrium. We're going to talk later today that since this isn't at equilibrium, we call that, instead of K, we call that Q. But we'll get to that later. You should remember that a little bit. What this is anytime you're not at equilibrium, we would call that Q, and that's how you determine which direction it will shift. So if we figured out that our concentrations were this, and we found that Q was less than K, what could we say? Is this going to shift left? Is this going to shift right? Is it going to shift? Why would it shift right? Because you need more products, right? You need more on the top than on the bottom to get to 16 if you're at 2. Okay? So what we then could do is we could set up really kind of an equation here. We could say 9 minus x, 12 minus x, x, and x. Okay? Because how this changes is going to affect how that changes, correct? We can take and we can plug that in. That's right. 16. Could you solve for x? Now this would actually be a little bit of work. Not a ton of work, but okay. But you could solve for x here, correct? Now we can just plug and chug in this situation and figure out what works. It's 8. Have you guys figured that out yet? Yeah, it's 8. Okay. So if I took 9 minus 8, 12 minus 8, you would get what? 1 and 4. And then you could have 8 and 8. And that should give you 16. So we knew it was product favored, and now we know how much product favored. It's almost all the way to completion. Why do I say almost all the way to completion? How much reactants are left over? Right, I still have one molecule of my starting, what was it, O3. And so I didn't completely react all of it. I fell one molecule short, but I would say that this reaction still lies really far to the right. Okay? Now we are going to do this with more complicated things when we have coefficients. Okay? And we're going to do this with math and not just in theory here. But I wanted to show you just the idea that we should be fairly familiar with the fact that there is a relationship that the products have to the reactants with those coefficients. And if we know that, we should be able to predict quite a few things. So, we've kind of already stated this, but if I had a large K value, what would that tell you?
The equilibrium is most products.
You looked at the didn't you?
I did.
Does that make sense though, based on what Grant illuminated a little bit ago?
As far as-
Okay, so really you've got above 1 and below 1. Does that make sense? If it's above 1, you're going to be product favored.
Right.
The further it is above 1, the further it is, or the closer it's getting to completion. Does that make sense? Okay. The low, when it gets below 1, the lowest it can get below 1 will tell you that it's really, really far left or reactant favored. Okay, and that is what this next slide is telling you. Okay, the tendency of a reaction can be stated by the K value. Large K means equilibrium is going to be far right or mostly products. A small K value means it's going to lie far left or mostly reactants. Now, something that's really important. The size of K, which I just talked about, really high meaning product favored, really low meaning reactants favored, does not tell you anything about how fast it's going to reach equilibrium. What tells you how fast you're going to get to equilibrium? Kinetics, last chapter,
Yeah.
right? We can have a K that's extremely high, but we know from last chapter that doesn't necessarily mean that it happens fast, right? Okay, so don't think that high K means fast. Think of high K just meaning it's going to go really far to completion. It could happen fast, but it could also happen slowly. Okay, so what is it that determined how fast the reaction would occur from last chapter? A little review here.
Number of yeah, like that. One thing.
One vocab word, pretty important vocab word from last chapter that we spent a good amount of time talking about when we said
Concentration.
rates are dependent upon its ability to what? Yes. How fast was determined? Well, we talked about a catalyst, right? The
Yeah.
catalyst speeds up a reaction, right?
Yeah.
And how did it do it?
Activation.
With a what?
Lower.
So how fast was primarily dependent upon the activation energy. Oh, really?
That's the lesson I missed.
Okay, so here's the thing. The magnitude, or how big K is, really depends on, doesn't only depend on this, but it depends a great deal on your change in E. For example, if you've got a really exothermic reaction, it's probably going to be heavily product favored. But if you have an endothermic reaction, it's probably going to be heavily reactant favored. However, the speed of it, now it's not the only factor, but it is a pretty important factor when determining whether it's really favorable thermodynamically. Okay? So, just a quick little reminder that our K value is going to be primarily, not only, but primarily determined by the fact, the energy difference, exo versus endo. Okay, because we know things react to become what? Stable. The more stable it is, the further it's probably going to progress to the products. That make sense? You have a question? You look like you're about to ask a question.
Well, in biology, botany, we're talking about photosynthesis, which is a very endothermic reaction because it's producing sugar, which is broken down later for energy.
Uh-huh.
So what is that mean it's the inefficient reaction then? Is it just
inefficient.
But it's reacting, you think it's reacting favor?
It might be true. I'd have to look more into that. But in theory, like if you're saying it's really endothermic, so therefore you're probably don't produce as much products as maybe you would have liked. There are some other factors that go into it. Okay?
Maybe natural catalyst or something like that. I don't know.
Probably. I'm sure there's.
Chlorophyll probably has something.
Yeah, I'm pretty sure there's some catalyst in there that makes it be a little bit more thermodynamically favorable. Okay. I was going to show you a picture out of the book, but it's just an energy diagram that showed the activation energy or change in E all over again, just to kind of make the idea that the rate is dependent upon its ability to get over the hump, and whether or not it's product favored or reactant favored is primarily dependent upon what your change in E is. Okay? So reaction quotient, I talked about this earlier, Q. It's obtained by basically doing your equilibrium expression, but when you're not at equilibrium, we don't call it K, we call it Q. So if I gave you a group of concentrations and I ask you, tell me if it's at equilibrium, you plop it into the expression you solve, and you find out that the number is not your K, it's Q. Now what's the importance of that, do you think? Well, why would we talk about Q or deal with Q at all?
Until it's less.
Yeah, like if it's less than K or greater than K, it could tell you which way it's going to go, or which way it's progressing. It hasn't stopped yet, but it might mean that it's either slow or you figured out the concentrations before it reached equilibrium. Now what if Q and K were the same? It's at equilibrium. And you should remember this from last chapter. When Q and K are equal, we know that the concentrations that you have at that point are your equilibrium concentrations. Very good. However, if Q is greater than K, you know it's going to shift left. Why? If Q was 14 and K was 10, why would that tell you you're gonna need to shift left?
It's more product favored than an equilibrium is.
Yeah, it has more products than it should have at equilibrium. So if it has more products than it should have at equilibrium, it's going to react those products to produce your reactants. And the same logic can be used when Q is less than K. You need more products to get a higher K, so therefore you've got to progress to the right. All right, now what I want you to do is I want you to find Q and predict which way it will shift to end the day. You guys understand what you're doing here?
That's what we've been doing, right?
Yeah.
Okay.
Gives you your concentrations. You got to figure out are you at equilibrium or not by plugging in and seeing if your values give you a K or not, and if it doesn't, predict which way it will shift.
Yes. I did it right.
Yeah.
Yeah. Constants in this are not the same. Okay, so it's not just me.
What?
Yeah, like ginormous numbers. Like, did we do this right?
For the first one?
Yeah.
This one?
It's called 500,000. On the dot net, the copies for me, it's really annoying to be large numbers.
Yeah.
I got that one.
It's the same.
But even then, that number doesn't, number 16.6. Oh, you are synthesis of ammonia. That means producing.
Does that make sense? The next one, I think,
No?
You said no.
Yeah. Maybe. You want to make that risk on a test, you go ahead.
I won't.
Where are you at?
Yeah, it was.
What?
I wonder if you guys can
I was guessing last one.
Yeah, it's gotta be, right? Mr. Kramer would, you know, give us shift right twice.
When on like the lab test, it's like true, false, true, false, true, false, true, false. And then the last thing, we're like true, 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 but switch.
Though I am the one that true false wrong because on my quiz he marked all my answers wrong. Yeah, he marked it wrong even though I had the right answer on my quiz. So I thought I had the wrong answer. So it's the other one on the test. So I just missed points for both. They gave it back to me on the quiz.
Almost done?
So when you're saying it needs a shift, you say shift the opposite way.
Left, shift right.
Yeah. Like, so if it's bigger than it, you want it to shift left. Shift left.
If Q is bigger,
Yeah. Yes. Okay. You don't say that Q is. You wouldn't say shift right, just say that Q is bigger. You say shift left.
yeah, you want it. Which way would it shift to get to K?
Okay, yeah.
Yep.
Yep.
Grant, you done? What'd you get on the first one?
Shift left.
What was the Q?
To like 12.
Oh,
1,500,000.
Yeah, it was a lot. Okay? It was 1.3 times 10 to the 7. Okay, so basically 13 million. Okay? Rylan? What'd you get for the second guy?
It was basically 6 times 10 and negative second.
Okay? So pretty much you would say what?
At equilibrium, or really close to it.
Yeah. If you're that close, just assume that you're not going to shift and you're at equilibrium. Okay? And when did you get the last one? You didn't get 2? You're struggling on that 2.
I mean, no, that's not. Yeah, and 2 plus 3, 2 plus 3.
Yeah, that's right.
Chemistry's fun.
6 6 times 10 to the negative 2.
You have no
Oh,
idea
no,
where
like,
you're
wow.
going.
Sure, that's
They all
makes sense.
They've done the run equation.
Or you just did the wrong
Okay,
concept.
Annie,
rounded wrong.
did you get through, or C? What'd you get?
Didn't run. Oh,
Yeah.
.002, so you would say shift right. Okay? So, a little bit of stuff today. We talked about how we're going to get to the process of looking at the coefficients and being able to predict mathematically what our equilibrium will be. Then we talked about Q and how if you plug in concentrations, you can find out whether or not you're at equilibrium if you know K. Then we talked about what a high K and what a low K means. What does a high K mean? Okay. And a low K? And does that mean if you have a high K that you got there really quickly?
No.
Could mean that, but doesn't necessarily mean that. So what determines how fast?
Activation.
Activation energy. And what determines how favorable? Your thermodynamics, or a big part of that would be your change in heat. Okay?
What was that?